I always like to say, there's two types of people in this world. There's people who think nuclear is incredible, and there's people who haven't looked into it closely enough yet. So if you have not looked into it closely, please do. And I think you'll be shocked by how incredibly cool and sexy this form of energy really is.
Hey everybody, this is Joe. We're here at Aalo Atomics in Austin, Texas, and I'm here with Matt Loszak, and he is the CEO of the company, and you have a pretty ambitious and kind of big plans coming up. So first of all, thank you very much for having me here and sharing with the viewers. And a second, can you talk a little bit about what is it that you guys are planning on doing?
Yeah, absolutely. Well, thanks for coming by, Joe. Appreciate it. And so what we're doing is we're building the world's first small nuclear reactor factory here in Austin. So these things are roughly the size of a shipping container, and each one is 10 megawatts electric.
Okay.
So what that means is it can power 10,000 homes, or a small data center, or a desalination plant. And the idea is we're going to be making these by the initially dozens and one day hundreds per year. And the idea is that this will be a number of reactors deployed into a fleet so that you can actually have super high availability of power, meaning instead of having one large reactor, which if you have to put it down for maintenance, you lose the whole generation capacity of the plant, we'll have a fleet of say 10 or 20 of these for 100 or 200 megawatts. And in doing so, you can achieve kind of an N+1 configuration where you have one or two that are there for backup. And for a data center or any kind of microgrid that requires super high uptime, this is a really unique solution because it's base load, it's clean, and it's super, super high availability.
Okay. Well, I think most people, when they think of nuclear reactors, they think of this gigantic structure with concrete cooling towers and gigawatts and gigawatts of electricity with thousands of people working on it. This is considerably different. You call it kind of like miniaturizing it and putting it onto a trailer. So where did this idea come from, and what are you building on to make this happen?
So essentially, there's always been a bit of an interesting debate in the nuclear industry because reactors, they did start off smaller. So there were a number of military reactors, maybe 70 years ago, 60 years ago, which were about this size. They fit on a truck. They were deployed for remote locations and so on. One powered a base kind of 40 feet below the ice surface in the Arctic, and then there were others in other remote places. But for good reason, reactors got larger. And there's better neutron economy, there's the larger pipe diameters, there's higher turbine efficiency. So there's a lot of reasons why nuclear plants became larger. But the issue is costs actually, after they decreased, started to go up again, especially in the West. And what we're really trying to do is fight this by trying to find the optimal balance of economy of numbers and economy of scale. So our thesis at Aalo is that when you go larger, there is also a diseconomy of scale at some point. And when you build a plant that takes 10 or 15 years to build, it's very difficult to have learnings that pass on from plant to plant to plant that can make it much more efficient. So the idea is if you can factor out a lot of that knowledge to a factory, and essentially this has not been done before, a factory that makes small reactors very repeatably with design for manufacturability built in from day one, then you can really try to achieve that optimal balance between economy of scale and economy of numbers. So that's what we're trying to do. And the first product we have is the Aalo 1. So this is a 10 megawatt electric reactor. And the reason we chose this size is because it's kind of the smallest size that can be commercially viable from an LCOE perspective. But we are not thinking that this first product would be the one that achieves our mission of 2 to 3 cents per kilowatt hour. So that would be the Aalo 2, our second product. And we think that will be somewhere in the ballpark of 100 megawatt electric. And so if you deploy a fleet of 10 Aalo 1s, you get to about 100 megawatts. And if you deploy a fleet of 10 Aalo 2s, you get to a gigawatt. And for us, for our design, to achieve 100 megawatt electric is only a little bit physically larger, but you get 10 times the power output. And so it's still very factory manufacturable, very modular, but we think that's kind of where the optimal balance will be from between economy of numbers and economy of scale. But yeah, for now, the 10 megawatt one is a good place to start because it's venture financeable. There's still a market for it. So that's why we start there.
Okay, well, that's pretty cool. And the whole idea of modularity with nuclear, even though you say that this is not brand new. I mean, it's technology that we started with a long time ago, and I think even in the 60s there was a lot of work on this, but it's really a new concept now because it's basically becoming feasible. And your particular design is not something that you just came up with and it's not been proven. It's actually based on some research and actually some work on building one here recently. Can you talk a little bit about that?
So our co-founder and our CTO is Yasser Arafat, and he was previously at Idaho National Lab where he was leading the MARVEL program. So this was a government reactor, a test reactor that was relatively small, so 30 kilowatt electric. And importantly, the program started in 2020, and very rapidly, in around 2.5, 3 years, the design was finished, the funding was put into place, and the first ever DOE authorization was achieved for a new advanced reactor, essentially since the DOE was formed in 1977. So that was a big milestone. And once MARVEL got approved, so now it's under construction as we speak, the fuel is being fabricated. And what we're doing at Aalo is commercializing a scaled up reactor inspired by MARVEL. So there's a number of changes you have to make to scale this up and make it more commercially focused. But that's kind of the core premise, is we're taking a technology that is pretty high TRL and taking it further to be much more economics and commercially focused.
Okay, well, if you follow me and my channel a lot, and with what Elon says is prototypes are easy, production is hard, and you're moving into that production idea of being able to mass manufacture these and be able to get them out in a modular way. Can you talk a little bit about just the basic design of your reactor and how does it work?
Yeah, absolutely. So essentially, it's a sodium-cooled reactor, thermal spectrum. So often you'll hear sodium fast reactors. This is different. The way that we achieve this thermal spectrum is with a special fuel called uranium zirconium hydride. This fuel is sometimes known as U-zirc hydride, also known as TRIGA fuel. And the special thing about this fuel is that it's often used in university research reactors, and they let students operate with this fuel. And essentially you can pull out the control rod, which is the part that slows down the reaction. So pull off the brakes basically, and you can do that as fast as you want. You can almost pneumatically eject it. And the fuel will heat up, but then essentially it will shut itself off. So it has this amazing inherent safety characteristic. And you might be wondering, if this fuel is so amazing, then why has it not been used for power production before? And the reason for that is because this fuel does not pair well with water. And all the reactors around the world today are water cooled essentially. And water can't take the heat away fast enough. So essentially the fuel is too safe, it's too finicky for use with water as a coolant. And that's why it's used in these university research reactors with water as the coolant. They're not doing power production, they're just trying to test the behavior of the fuel in this circumstance. But when you combine this fuel with liquid metal like sodium, it's a match made in heaven. It's really a beautiful pairing because the liquid metal can take the heat away fast enough to use this fuel for power production. So you get a really good high energy density, but you still maintain the inherent safety properties of the fuel. And for us at Aalo, if we're trying to mass manufacture nuclear reactors to be all over the place, we believe that they should be as safe as a university research reactor, which many of you watching this video might not even know exists in the US, operating right on university campuses. And students walk by these things every day and they don't even know that there's a nuclear reactor right next to them. So in our view, if you want to make nuclear ubiquitous, it's got to be as safe as that, such that it could be in your backyard and you wouldn't even know it was there.
Well, some people, that when they hear nuclear, they think, bombs and big things and all that stuff. But essentially what you're building is a giant heat engine. You have something that heats up, in this case, your fuel. And it's actually kind of neat because your mixture is both the fissional material, but also the moderator for the neutrons. And that is one of the reasons why, as it heats up, if nothing else is done, it shuts itself off. And then you use the sodium as your coolant. But that coolant gets hot, so it needs to go somewhere. So you're going to turn that into something. So if I understand it, it's going to be thermal energy that you're going to be able to produce, and also electrical energy. So can you talk a little bit about how that works?
Yeah, absolutely. So you make a really good point. It's worth highlighting that this reactor configuration is pretty special because it's what's called homogeneous, meaning the moderator, so that's the thing that slows down the neutrons to the speed where they can interact with the uranium-235 and cause fission. The moderator is in the same atomic space as the fuel, which is where the uranium-235 is. And so that's why you get this really, really fast response where when the moderator heats up, it becomes less good at moderating, and therefore more neutrons leak out and cause less fission, which slows the reaction down. And in most other reactors around the world today, the moderator is the water, which is the coolant. So in our case, the coolant is the sodium, and the sodium is just cooling. It's not moderating. So there's a difference there, and it's kind of cool what happens when you, no pun intended, cool, where you combine the moderator into the fuel. So that's a big part of it. And so then you have the coolant, the sodium, the liquid metal is circulating around. It's being pumped through the reactor core. And because, you know how when you touch a metal, it feels cold, right? And that's not because it is cold, if it's been sitting out in your room for a while. It's at room temperature. But it feels cold because it's taking the heat away from your hand quickly. So it's a really beautiful material for that because it just takes heat away so fast and allows you to use less material and achieve the same outcome, which is taking heat away and rapidly moving that towards the turbine to spin something to generate electricity.
Okay.
So in our reactor, we have a sodium loop and then another sodium loop, and then we have a loop of water, which is getting boiled and turning to steam and turning a turbine. And that rotational energy is what you can directly translate into electrical power. Or you can also just take the steam, which is very high temperature. Because the sodium has a higher boiling point, you can achieve a higher temperature that is coming from the reactor core, so something like 500 Celsius, and use that for some industrial processes. It might be worth mentioning that current nuclear, it kind of caps out around 300 Celsius if you just take the steam straight from the reactor. And because ours goes higher, we can decarbonize a wider array of industrial processes.
Okay.
This has not been explored much yet in the nuclear industry, doing much decarbonization of industrial process heat, but it's on everyone's radar. And at that temperature range, you can decarbonize roughly half of all the industrial process heat applications out there. So it's a little tricky to do things like concrete or steel or glass, but there are quite a few chemical processes that can be decarbonized with this temperature of steam.
Well, that's pretty cool. So not only do you have this capability of making, with a small compact unit, heat energy and also electrical energy, it's modular. Where do you see this being used, and how do you, what is your, I guess, your business model of people that are going to be using this product?
Our plan kind of breaks down into 3 different stages. So first, we intend to make slightly more expensive, first-of-a-kind nuclear reactors for wealthy customers who are desperate for the energy. So this would be data center companies, big tech companies. The LCOE will be a little bit higher than it otherwise would, but that's okay because they are so desperate for power. This is largely driven by AI demand, but you've also got things like electric vehicle charging, heat pumps. All sorts of new demand is coming up that requires more electricity. So that's phase 1. Phase 2 is then once we come down that cost curve, we achieve an LCOE, a levelized cost of electricity that is kind of in the ballpark of what a lot of utilities in centralized locations require. then we'll sell these fleets of these reactors to those utilities. And one day, the phase 3, the really aspirational goal, is to get this to a point where within the first few years of deployment, you're hitting the 2 to 3 cent per kilowatt hour mark. And it's worth saying, this is part of the mission of the company. And nuclear today, if you take one of those big gigawatt scale nuclear reactors that's already paid off and has been around for decades, you can do a refurbishment and so on. If you break out the LCOE in that period, it's actually already 2 to 3 cents. But the challenge is, can you build new nuclear and within those first 10 or 20 years hit that price point of an LCOE? That's the real challenge. And if you can do that, then you can, and as long as the geopolitical relationships are in place and we're seeing an evolving situation there, then our phase 3 would essentially be deploying this around the world and helping a lot of third world countries to essentially leapfrog right to a clean baseload energy source that really doesn't require much land or resources at all. So that's the eventual phase 3 goal of the company.
Okay. Now, some people may be wondering, but you're doing this in cooperation with the U.S. government. I mean, Department of Energy and I think the Nuclear Regulatory Commission, they're part of this process. They're encouraging companies like you to explore this. Is that correct?
Yeah, absolutely. So we've had great support from the DOE and NRC thus far. So we submitted our regulatory engagement plan to the NRC. We're currently engaged with them and we're making good progress there for our first commercial deployments. And then we've also got some good progress with the Department of Energy. We signed a site use MOU with them to use a certain plot of land at Idaho National Lab where Marvel is being built. And this is also actually where essentially the first atomic age got started. So at Idaho National Lab, there were 52 test reactors that were built there in the 1950s and 1960s. And the sad thing is, at the end of that atomic age, it went down to just 3 reactors. But Marvel is amongst the first to go live. It's going to be going live in the next year or two, and that's kind of the dawn of this second atomic age at Idaho National Lab all over again. And ours will shortly follow thereafter. And so that was a big part of our DOE support with the DOE setting MOU.
Okay, yeah, I would say that your work basing it off of the Marvel with the proof of concept and also with their work with the DOE, that's kind of helped speed you along to where you're at. Now you have a lot of links with Idaho, but you're here in Austin. So why are you here in Austin? What's the deal?
Yeah, fair question. So we have 2 main offices. One is in Idaho Falls and one is in Austin. And what we've really tried to do is bake into our DNA the ability to make reactors in a centralized facility like here in Austin, and then ship it all around the country and one day the world. So the idea that our first few deployments will be in Idaho, near Idaho Falls, and a lot of our manufacturing happening here is really just to make sure that from day one, we're set up in such a way that we can actually test that hypothesis and say, it's one thing to think you can build a reactor that you can ship easily and install somewhere else, but it's another thing to do it or set yourself up in such a way that you have to do it. So that's really what we're thinking there. And there's a beautiful reason to have a strong presence in Idaho Falls. I mean, there's a lot of amazing nuclear talent there. There's a lot of people we can recruit, but also work with on the other side of the fence with INL or DOE. And that's a beautiful place to build our first deployment because, for the reason we already said, I mean, it was the dawn of the first atomic age that happened there. And then here in Austin, it's got an amazing talent base to recruit from as well. There's a big history here with the Giga Factory, and a lot of amazing manufacturing happens here. But also, so Texas has this history of innovation in energy with oil and gas, fracking. I mean, arguably the whole natural gas progression from being trailing behind coal and now surpassing coal as of something like 2016 to be the largest electricity producer in all of the country. That would not have happened without the innovations that happened here on fracking. And we think that Texas should and will play a massive role in innovation in energy in the next couple decades. And we're already seeing it. The politicians here in Texas are very pro-nuclear, and the same cannot be said of some other places, maybe California. And so, yeah, those were our main reasons for setting up these 2 locations.
Okay, well, one last question, and then maybe we'll go out and take a look at your facility. You mentioned Gigafactory, and you're kind of basing your plans on how a Gigafactory works. So how does that concept play a role in what you're trying to do here?
So there's this concept of design for manufacturability that we're really trying to embed in the culture in the design from day one. And so, right now we're setting up our pilot line. This is going to have a production capacity, we believe, this is our target, of several dozen reactors per year of the Aalo 1 model. But certainly over time, we have this space for a while, and we've spoken to a bunch of folks who have led manufacturing at companies like SpaceX and Tesla and others. And our belief is that even within the square footage that we have here, so 40,000 square feet, we could be producing in this space upwards of 100 reactors per year.
Okay.
And if that is the Aalo 1 product, then that is a gigawatt in capacity every year. And I mean, there's a gigafactory down there, but this would be kind of like a gigawatt factory.
Okay.
A gigawatt per year. That's a good target for this space. So.
All right, well, why don't we go out and take a look at your space, and maybe you can talk a little bit about what your plans are by looking at that.
Cool, let's do it.
All right, cool. Okay, so we've come out to your main facility, and as you can tell right now, it's a little empty, but you have some big plans. So you want to talk a little bit what you are going to be doing here and how you're going to organize this area.
Yeah, absolutely. So we just moved here about 3 weeks ago. So right now the space is fairly empty. But within around 6 months, we intend to have essentially a full-scale non-nuclear prototype completed. So we got the bay doors down here, and this is where we'll be receiving a lot of the raw materials. Our reactor really is just a lot of stainless steel. There's no kind of unobtainium or materials that are going to be more difficult to procure, and that was very much by design. So along this wall here, we're going to have water jet, we're going to have some welding equipment, essentially everything required to take large sheets of stainless steel and manipulate this into cylinders in the correct shapes for the creation of this reactor. Down the middle, we're going to have the assembly line. So this is where we're taking a lot of the subcomponents and assembling them into the finished product. And on the far side, you've got a bit more office space. We're going to expand down there. Of course, you've got the large American flag. That was pretty critical.
Yeah.
Over here right now, we're setting up for the grand opening. So we're hosting 100 different people from politics and the nuclear sector and the regulators and investors, the company. So everyone's coming down, and we'll have about 100 people here to do the grand opening, celebrate getting the new space and this next chapter of the company's history. So.
All right. So your grand opening is coming up on Monday. That's what, the 23rd of September. Then you're going to get right to work. When do you think you're going to start producing your first demonstration item?
Yeah. So our target ambitiously is to get authorization to produce the first reactor and install it at a site within around 18 months. So right now, this looks pretty empty, but yeah, if you come back over the next 18 months, I think you'll see a lot of rapid progress. But that is our goal, is in 18 months to begin construction on the first real reactor.
Okay, now you mentioned Gigafactory and using some of the principles associated with Gigafactories, and one of those is vertical integration. So you can talk a little bit about your plans for vertical integration and what you're going to be building.
Yeah, absolutely. So initially for the first non-nuclear prototype, it'll not be very vertically integrated. So we're going to do a lot of the assembly here ourselves, but then purchasing certain components from other manufacturers in the area, like APE, which is a great partner of ours, and a number of others. But very shortly thereafter, we're going to vertically integrate a lot of the manufacturing of a lot of those subcomponents, and there will kind of remain one or two larger complex pieces that we will still outsource. But certainly at some point in the next few years, we intend to essentially fully vertically integrate those parts as well. So if you keep returning in the next few years, you'll probably see that unfolding. But currently that's the plan, is you got to figure out how to go from point A to point B, and right now this is our strategy. Okay.
Now you mentioned that one of the good things about Texas is it's got an installed base of all kinds of people that have experience, even then from the oil and gas business. And ironically, even SpaceX took advantage of that when it had to do with welding and making tanks, which look like rockets now. What kind of people or what kind of skills are you looking at, and are you hiring, and what would people need to be able to know to be able to try to work with you?
Yeah. So we've done a lot of hiring recently. In the past month or two, we've hired about 15 people. This is kind of doubling the team size from where it is today. But over the next couple of years, we're going to double the team again. And so if you're living near Texas or interested in moving to Texas, because we want everyone to be here in the factory space with us, definitely let us know. If you are good at metal manipulation, welding, any kind of manufacturing that you've done in the past, definitely reach out to us, and we'll take a look and see if we can work together.
Okay, and you don't have to be a nuclear engineer to come work for you, is that right?
Yeah, I mean, so right now there's about 100,000 people in the nuclear industry in the US, and there are some estimates that say to hit our targets by 2050 for this whole energy transition, we're going to have to triple that to 300,000. So, by definition, we're going to have to recruit a lot of amazing people from outside the nuclear industry, and we've already done a good amount of that. So we've got some folks already from several other industries, and we've got to do a lot more of that. But I think it's kind of cool because, in the 1940s and 50s, a lot of the top kind of brains in the world were focused on physics and energy and things like that. And then there's kind of this mass exodus towards internet and transistors and computer technology. And now there's been AI, crypto, you name it. But I really believe that energy is going to be this insanely exciting, cool space that is going to have a lot of momentum and excitement in the next decade or more. And so I would highly recommend checking it out if you haven't already. And yeah, I always like to say, there's two types of people in this world. There's people who think nuclear is incredible, and there's people who haven't looked into it closely enough yet. So if you have not looked into it closely, please do. And I think you'll be shocked by how incredibly cool and sexy this form of energy really is.
All right, well, the next step for you is the grand opening coming up in just a couple of days. We'll be back here for that, and viewers will get a chance to see what that is looking like. So thank you very much for your time and for talking a little bit about what your plans are. They're very ambitious, but I do hope the best for you. I think there's a bright future for what you're trying to do.
Amazing. Yeah, thanks so much for coming.
Thanks.
Yeah.